Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 18th video lecture. And today we're going to do the proof of the integration by parts theorem, which we had stated before but hadn't proven. And we're also going to move on to integration of vector value functions. And most of the statements that we'll have today are analogous to statements that we've had about non-vector value functions in terms of integration. And we won't even do proofs for most of the statements that we have today, but there will be two theorems that we'll state that we will prove for vector value functions during this lecture. Okay, let's start off with the integration by parts theorem, and here it's written behind me. It says, suppose f and g are differentiable functions on a to b, and the derivative of big F is equal to little f, and that derivative, or little f, is Riemann integrable, and the derivative of g, which is little g, is also Riemann integrable. Then the integral, the Riemann integral from a to b of big F times little g will be equal to big F evaluated b times big G evaluated b minus big F evaluated a times big G evaluated a minus the integral from a to b of little f times big G. This integration by parts can be thought of as the anti-product rule. All right. Let's look at its proof. So, as its proof, we'll let big H of x be equal to big F of x times big G of x. Okay. Now, we're assuming that F and G are differentiable. So, since big F and big G are differentiable, on the closed interval from a to b, then that says that big F and big G are continuous. On a to b. And we had learned earlier that if you integrate a continuous function, well, if you try to integrate a continuous function, you can. Continuous functions are integrable. So that means big F and big G are Riemann integrable on a to b. And so H is Riemann integrable on a to b because it's the product of integrable functions, and we've proven that the product of integrable functions is integrable. So I'll say H is Riemann integrable on a to b with that sentence. Also, if you'll notice that the derivative of H, okay, so I'd use the product rule. So I'd write down the first, that's the derivative of the second, plus, now I write down the derivative of the first times the second. Now, here we've said that F is integrable. G prime, which is equal to little g, by assumption it's integrable. Big F, I should have written X here. Big F prime is equal to little f, and that's integrable. And G, being continuous, is integrable. So since all those are Riemann integrable, then you multiply Riemann integrable functions together, that's Riemann integrable. And if you add two Riemann integrable functions together, that's Riemann integrable. So H prime is Riemann integrable on a to b. Thus, by the fundamental theorem of calculus, part 2, the interval from A to B of h prime of x is really going to be equal to h evaluated at B minus h evaluated at A. That's what it's going to be equal to, but I want to back up just for a second. So instead of saying that, what we'll say is equal to the integral from A to B. We'll write down what h prime is equal to, which is f of x times big G prime, which is little g of x, plus g of x times big F prime, which is little f of x, dx, which we can split up into two integrals. So it's the integral from A to B of f of x times g of x dx plus an integral from A to B g of x times f of x dx. And that indeed does equal to h of b minus h of a, okay? Because of for the fundamental theorem of calculus. So we're using some other theorems we have as well about integration besides the fundamental theorem of calculus in this statement. So that's what we are. Okay. So, it's very cloudy, so I figured it was in the post. So, what we get is that the integral from A to B of f of x times little g of x will be equal to h of b minus h of a by our previous work, and then minus the integral from A to B of g of x, big G of x, times f of x dx. Now, just replacing h of b by what it's equal to, that's f of b times big G of b, by definition of what f is, what h is, minus f of a times g of a, minus this integral from A to b of, I'll rewrite this just as f of x times big G of x dx. And that's what we wanted to show. So that proves integration by parts for me. Well, next I want to give a definition for how we do integration of vector value functions. So here's what we have. We let f1, f2, all the way up to fk be real functions on A to B, and let f bar be equal to f sub 1, f sub 2, all the way up to f sub k is 2. B, the corresponding mapping of of the closed interval AB into Euclidean space. So if alpha is monotonically increasing, on A to B, Then, we're about to make our definition. F bar to say F bar is Riemann-Stieltjes integral means that F sub j is Riemann-Stieltjes integral for j equal 1, 2, all the way up to k, and that's the definition. And what we mean is, in this case, we define the integral from a to b of f bar. Let's call it f bar of t dt. Shouldn't say bt, d alpha. Let's just say f d alpha. We define it to be equal to the integral from a to b of f1 d alpha, integral from a to b of f2 d alpha, all the way up to the integral from a to b of fk d alpha. So that's the way that we're defining the integral of a vector value function, f bar, where the output values are a vector in Rk. So what we're saying here, in other words, that this integral from a to b of f bar d alpha, that is a point in Rk where the j coordinate of this integral, of this point in Rk, is, so the j coordinate at this point, is the integral from a to b of f sub j d alpha. And just as a comment, as all definitions are, this definition is an if and only if statement. So if the component functions are all Riemann-Stieltjes integrable, then the vector value function is going to be Riemann-Stieltjes integrable, okay, and vice versa. Okay. So as a comment, many theorems about integration of real value functions have analogous versions with regards to vector value. Functions. Okay. And they're proven in analogous ways. by applying. Yeah, I should say that not only they're it's not that they're proven in analogous ways, but we apply the real value theorem to the component functions. Of the vector value function f bar. So as an example, let's look at the following theorem proof. So here's the theorem. It says if f bar is Riemann-Stieltjes integral where f bar goes from A to B into Rk. So it's vector value. And C is a constant. It's not one of the real numbers. Then C times F is, C times F bar, I should say, is Riemann-Stieltjes integral. And not only does that happen, but the integral from A to B of C times F bar d alpha will be equal to C times the integral from A to B of F bar d alpha.
So let's look at the proof.
So we let f bar be Riemann-Stieltjes integral, where f bar is equal to f sub 1, comma f sub 2, comma f sub k, and we have C is a real number. So since f bar is Riemann-Stieltjes integral, then that means each one of these component functions is Riemann-Stieltjes integral. So I'll denote that as f sub j is Riemann-Stieltjes integral on it with respect to alpha on A to B for all j element 1, 2, all the way up to k for each component. So that means CFJ is an element of the Riemann integral functions, Riemann-Stieltjes integral functions on A to B for all j element of 1, 2, 3, all the way up to k. Because we proved that anytime you give me a real value function f sub j that's Riemann-Stieltjes integral, then a constant times it will be Riemann-Stieltjes integral. And not only that, so this is by a previous theorem. Okay. And by that same theorem, we're going to get the result we want. The completion of the result we want. Okay. That is, we know this guy exists. So integral of c f bar d alpha. Not only do we know it exists, here's what it's equal to. It's equal to this k tuple, which is the integral from a to b of cf1 d alpha, integral from a to b of cf2 d alpha, all the way up to an integral from a to b of cfk d alpha. But for each one of these components, the c can be taken out. So the c can be taken out of the integral from a to b, f d1, f sub 1 d alpha, comma, c integral from a to b of f sub 2 d alpha, all the way up to c times the integral from a to b of f sub k d alpha. Now this is a k tuple, so it's a point in Euclidean space, and we can pull out the c from each of the components here. We have c times the tuple, whose first component is the integral from a to b of f sub 1 d alpha, and the second component is the integral from a to b of f sub 2 d alpha, integral from a to b of f sub k d alpha. But each one, or this k tuple, is nothing more than the integral from a to b of f bar d alpha. And that's what we were trying to show. So that is this proof. Okay, what I'm going to do next is I'm going to list several theorems in a row that are extensions of theorems that we've had about real valued functions in terms of integration. I'm extending them to vector valued functions in terms of integration. Now I'm going to do this without proof, so I'm just going to write down a bunch of theorems. But we will prove the last one. So, in other words, we now state some theorems about integration of vector value functions without proof. So these are things that you can prove. Here's the thing. It says if f bar is an element of Riemann-Stiel's integral functions with respect to alpha on a to b, and if a is less than c is less than b, then f bar is Riemann-Stiel's disintegrable on a to c and on c to b. And not only that, but the integral from a to b of f bar d alpha will be equal to the integral from a to c of f bar d alpha plus the integral from c to b of f bar d alpha. Again, I'm going to prove that. Here's another theorem. if f sub 1 bar is Riemann-Stieltjes integrable with respect to alpha, and f sub 2 bar is Riemann-Stieltjes integrable with respect to alpha on a to b, then f sub 1 bar plus f sub 2 bar is Riemann-Stieltjes integrable with respect to alpha on a to b. Not only that, but the integral from a to b of f sub 1 bar plus f sub 2, it should have a bar, d alpha is equal to the integral from a to b of f sub 1 bar d alpha plus the integral from a to b of f sub 2 bar d alpha. Again, this is a theorem that we won't prove. It's analogous to what we had for real value functions. Here's another theorem. It says if f bar is Riemann-Stieltjes integrable with respect to alpha sub 1, and f bar is Riemann-Stieltjes integrable with respect to alpha sub 2, then f bar is Riemann-Stieltjes integrable with respect to alpha sub 1 plus alpha sub 2. Not only that, the integral from a to b of f bar d alpha sub 1 plus alpha sub 2 will be equal to the integral from a to b of f bar d alpha sub 1 plus the integral from a to b of f bar d alpha sub 2. Another theorem that we'll state without proof is if f is Riemann-Stieltjes integrable with respect to alpha, and c is greater than 0, then f bar, should be bar, is Riemann-Stieltjes integrable with respect to c times alpha, okay, and that integral from a to b of f bar dc alpha is equal to c times the integral from a to b of f d alpha, f bar d alpha. Oops. Okay. Another theorem. If we assume alpha increases monotonically, and alpha prime is Riemann integrable on a to b, we let f bar be a bounded vector value function on a to b. Okay. Then still this integral with respect to alpha, if and only if f sub j alpha prime is an element of Riemann integral functions. Okay. Where j is equal to 1, 2, all the way to k. And again, f bar is equal to the function whose component functions is f sub 1, f sub 2, all the way to f sub k. We're not going to prove that one either. Here's another theorem. It says let f bar go from A to B into RK. Suppose f bar is Riemann integrable on A to B, and then for A less than or equal to x less than or equal to b, put big F bar of x equal to the integral from A to x of f, little f bar of t dt. Then f, big F, is continuous on A to B. Furthermore, if f bar is continuous, at x sub naught in A to B, then f, big F bar, is differentiable at x naught and f, big bar, big F bar, I should say, its derivative at x naught is equal to little f bar evaluated at x naught. So that's the fundamental theorem of calculus part 1 for vector value functions. And we also have the fundamental theorem of part 2 for vector value functions. Here that is. There's a theorem. If f bar and big F bar map A to B into RK, if little f bar is an element of Riemann integral, Riemann Stieltjes integral functions. No, just Riemann integral functions. And if f, big F bar's derivative equals to little f bar, then what we have is that the integral from A to B of little f bar dt will be equal to big F bar evaluated B minus big F bar evaluated A. Now, we're going to prove the next one, and what I want to say is that the following theorem offers some differences in its proof, so we'll look at it. So what theorem were we talking about? Well, this theorem. It says if F bar maps A to B into RK, and if F bar is an element of Riemann-Stieltjes integrable functions with respect to alpha for some monotonically increasing function alpha on A to B, then the absolute value of F is Riemann-Stieltjes integrable. It's the module, it's the norm on F bar. It's Riemann-Stieltjes integral with respect to alpha. And here the integral, I shouldn't say the absolute value, I should say the norm from A to B, norm of the integral from A to B of F bar d alpha, that will be less than or equal to the integral from A to B of the norm of F bar d alpha. Okay, so we want to prove this. We're going to start off by getting some notation down. So we're going to let F bar be equal to F sub 1, F sub 2, all the way up to F sub k. That's two component functions. Then, when someone says, what is the norm of F bar, that's equal to the sum, or if you will, the square root of F sub 1 squared plus F sub 2 squared plus all the way up to plus F sub k squared. Now, since our goal here is to show that the norm of F bar is Riemann-Stieltjes integral first. That's the first goal. And then we have this inequality we want to show. So we're working on the first part. Since F sub j is Riemann-Stieltjes integrable, and we know that because I'll just write it right here as F bar is Riemann-Stieltjes integrable with respect to alpha, then that's going to tell me that the square is Riemann-Stieltjes integral. Then f sub j squared is Riemann still this interval. Okay? And that's true for all j from 1 up to k. F sub 1 squared plus f sub 2 squared plus all the way up to adding up f sub k squared, that's going to be a Riemann still this interval function with respect to alpha. And that's extending a theorem we already had, that if you add two Riemann still this interval functions, you get a Riemann still this interval function. And here we were just adding up k of them, and so extending it to any number of functions being added can be proven using induction. And next thing we know is that since f sub j squared is Riemann still this interval, then f sub j squared is bounded so that means that f sub 1 squared plus f sub 2 squared plus all the way up to f sub k squared, that's going to be bounded. Say by big M, positive number. And so since the function g of x equaling the square root of x is continuous on 0 to m, then by a previous theorem, for real value functions, we obtain that the g, well, here I'll just say, so by a previous theorem, I'll just say then, the square root, so this is the composition of a continuous function with something that's Riemann still this interval, f sub 1 squared plus f sub 2 squared plus f sub k squared. That is, well, what that is the norm of f bar. Okay? That's, this right here is Riemann still this interval, making f, the norm of f bar, be Riemann still this interval. And so that's part of what we wanted to prove. Now we want to prove that inequality involving absolute values. That is, let me write that down, we want to prove that the absolute value of the integral from a to b of f bar d alpha is going to be less than or equal to the integral from a to b of the norm of f bar d alpha. We're going to do this using Schwartz inequality. So here, to get some notation involved that may simplify the proof, we're going to let y bar be equal to y sub 1, comma, y sub 2, comma, up to y sub k, which is going to be equal to the integral, the tuple that is the integral from a to b of f sub 1 d alpha, comma, the integral from a to b of f sub 2 d alpha, all the way up to the integral from a to b of f sub k d alpha, which of course equals to the integral from a to b of f bar d alpha. Now, what we'll do is we'll note that the norm, here I call it y bar, yeah, good, y bar squared, okay? Well, that's going to be, without the square, it's the square root of each one of these components being squared, but with the square, we don't have a square root here. It's just the sum as I runs from 1 to k of y sub I squared. Okay, but we can rewrite this as the sum as I runs from 1 to k of y sub I, and then I'll rewrite y times y sub I. But the way I'll rewrite y sub I is the integral from a to b of f sub I d alpha. Okay, so that's what we are. And what we can do is interchange these sums and integrals. And so that's equal to, as the sum, the integral from a to b of the sum, as I runs from 1 to k, of y sub I times f sub I d alpha. Okay, that's what we're on. Now, I said we were going to use Schwartz inequality in this proof, so let's recall it. And these were for complex numbers, sequence of complex numbers. It said this: if finite sequences a1, a2 up to an, and b1, b2 up to bn are complex numbers, then that norm, as I runs from 1 to n, of a sub I guess I call this j, so let's call this j and j here. B sub j's conjugate, that guy squared will be less than or equal to the sum as j runs from 1 to n of a sub j squared, that's the norms of those, squared, times the sum as j runs from 1 to n of the norms of the b sub j to b squared. And that's what we're going to use. Okay, so how are we going to use it? Well, we'll look at this. The norm of the sum as I runs from 1 to k of y sub I, f sub I. So remember, that's something we're integrating. That's where we left off. Okay? That's going to be less than or equal to, so this isn't being squared. So it's going to be the square root of the sum as I runs from 1 to k of y sub I, its norm, okay, but its norm is just squared here. No, it should be its norm. That's right, squared, times the sum as I run from 1 to k of the f sub i's, its norm being squared, absolute value being squared. Because we're talking about real numbers here, which is going to be less than or equal to square root of the sum as I runs from 1 to k. So here, this is a real number. And so its absolute value being squared is just it being squared. Again, here, this is just f sub I squared. And so what we did is that this absolute value here, as I runs from 1 to k, of y sub I, f sub I, is going to be less than or equal to, here this is the square root. This would be, this part right here would be the norm of y bar squared, and here this would be the norm of f bar squared. Okay, I need just a second. So, what we have is that the norm of y bar squared, which is equal to this will be the integral, that's what we had, from a to b of y sub I, f sub I. Okay. I'm sorry, I made a mistake here. This integral of the sum, so I runs from 1 to k, of y sub I, f sub I, is going to be less than or equal to the integral from a to b of the norm of y times the norm of f d alpha, okay, which is what's resulting from the line above. Okay. And so what we're saying here is that this quantity, which is just a real number, its absolute value, of course, is going to be bigger than this quantity, which is going to be less than, well, the square root of this is just the absolute value, or the norm of y, and the square root of f bar squared is just, I'm sorry, the square root of the norm of f bar squared is just the norm of f bar, so that's what we have. So that's what we were trying to show, and essentially. There's a little bit more. So, what we have is that the norm of y bar being squared is less than or equal to, well, we had this integral, okay, we had before. And we can factor out the norm of y, integral from a to b, of f of t's bars, norm d alpha. All right, now, we like to divide by this norm, but we may not be able to do that because it might be 0. So, case 1 is if this norm of y bar is not 0, then we have from here, the norm of y bar is less than or equal to the integral from a to b of the norm of f bar to f bar d alpha. That's what I write. And so, what is this? That's nothing more, remember what this was. This was the integral. Y bar is the integral. So it's the norm of the integral from a to b of f bar d alpha. It's going to be less than or equal to the integral from a to b of f bar d alpha. So we have it in this case. And then finally, in case 2, just in case that norm of y bar is 0. Yeah. Case 2. If norm of y bar equals to 0, then that would say that y bar itself must be 0. So that says that the integral from a to b of f d alpha, which is what y bar is, f bar d alpha, is equal to 0. And so since 0 is less than or equal to the integral from a to b of f bar inside absolute values d alpha, then the absolute value of the integral from a to b of f bar d alpha, which in this case is 0, is less than, is less than the integral from a to b of f bar d alpha. So that's what we have. So in all cases, all possible cases, the absolute value of the integral from a to b of f bar d alpha would be less than or equal to the integral from a to b of the norm. I shouldn't say absolute value, it is the norm of this. Norm of f bar d alpha. And that concludes the proof. That's enough for this video lecture. Thank you very much for your time and patience.